Good afternoon. Welcome to CS229. This is going to be lecture 5. We're going to talk about Gaussian discriminant analysis. So this is going to be our first foray into generative models. These generative models are pretty interesting because, they're the G in GPT. So you hear the chat GPT, it's generative pre-trained transformers. We will maybe do pre-training a little bit later, maybe transformers a little bit later. But today we're getting our first example of a generative algorithm. And intuitively what goes on in a generative algorithm is you try to learn a representation of your data. And you're going to see it in about the simplest form that we can do today. So you can see what that means to learn a representation of your data or understand that piece, and then how you can use that for discrimination. So you'll see the things, and we'll relate it back. So our plan is roughly as follows. We're going to talk a little bit about this generative versus discriminative thing that I've just been mentioning. These are a different class of these algorithms. I would say one kind of side note, when we teach these lectures, 6-7 years ago, whenever it was, when you talk about these generative models, people weren't that interested in the generative models because they didn't seem like they got to state-of-the-art performance, right? But now they get to, they are responsible for a lot of the growth in AI. And this fact that they're learning these representations is actually quite valuable, okay? All right, we're then going to talk about the Gaussian distribution. We're going to talk about the difference between how we go from 1D to 2D functions. And we're just going to introduce a bunch of notation. So hopefully this will be things that are familiar to you. But if not, don't worry. There's going to be a bunch of pictures. Now, I should warn you, I let Claude rewrite a bunch of the pictures and generate a bunch of plots. I hope they're okay. I checked them. But we'll see how it goes. I gave you a bunch of visualizations, so we'll see how that goes. We'll then have enough information to do GDA, Gaussian discriminant analysis. And then we'll do maximum likelihood for GDA. What will be interesting about this, which is not a general fact, but is interesting for this, is we'll be able to do estimation without having to do a lot of learning. And so, in fact, in many cases, in traditional SGD learning, we'll be able to do something fairly quick and dirty. And we'll also get exposed to how these MLE parameters are actually are estimated for generative models, which we'll use a lot as we go through and build up the rest of the hierarchy of Gaussian models. And so one thing I should just say about the kind of, if you're picking up on how the course is taught, we start with the most kind of simple setting that we can, and we're kind of relaxing one assumption as we go. So hopefully there's only one new moving piece in any lecture. But if you look back, you're like, wow, we've actually hopefully covered a fair amount of ground. I'm going to talk a little bit about the GDA decision boundary. I couldn't help myself here. There's one thing which I don't think is in the notes, but I just added in, which has to do with these things called quadratic decision boundaries, because the question has come up every time I've ever taught it. So I just put in visualization. Then I'm going to talk about the difference between GDA and logistic regression. These are the discriminative and generative versions. And we're going to see why classically people preferred logistic regression for many, many years. But as I said, that has switched in recent years. The importance of generative models, I would say arguably dwarfs the discriminative from the point of view of excitement, maybe not of utility yet. And then we'll talk about naive Bayes, which is one of the simplest generative models. We'll do a spam filter because I think there's still some law that we have to teach you how to build a spam filter. All right. Anyway, so we're going to move at a high level. So that's the overarching idea. We're going to move from modeling P of Y given X. That is, what is the probability of the label given the data point? That's what we've been doing discriminatively, to modeling in the other direction. What does the data distribution X look like given Y? Okay? And I'll make that concrete over this. All right. Awesome. This will be our first generative model. Okay. So all the algorithms we have seen so far are discriminative. They basically say something like linear regression. P of Y given X and theta was modeled as a Gaussian error, if you recall. Logistic regression, it was as a Bernoulli. But the important salient point of both of them is you were given X, you estimated some parameters, and then you decided which class that it was, okay? All right, we learned the exponential family, and that was just a generalization of the same story. So all of them, everything you've seen so far was discriminative. And in each case, we learned this X given Y. Now, intuitively, why does that make sense? Why are machine learning people so excited about that? Why do we do it? Well, it seems easier than learning P of X and Y at the same time. Now, why may that be? P of X and Y at the same time means the probability of your data and of the class. If your class, for example, is relatively simple to describe, you're classifying two things which kind of couldn't be more different, and they're really spread apart, you don't need to spend all your time learning the nooks and crannies of class A versus class B. And I'll come to an example of this in a second. You could probably learn how to separate them, right? That's what discriminators do all the time. Okay? That's what a discriminative model would do. It kind of tries to learn a separating boundary. We saw this again and again. All right. We're going to consider something else. Now, arguably, you should be able to tell the difference between cats and elephants pretty easily. And these are not actual data from cats and elephants. And I don't know why I picked cats and elephants, but I think it was dogs and elephants at one point, and then maybe Claude prefers cats to dogs and switched it before I redrafted these. Okay? All right. So here's what we're going to do. We're going to look at our generative model. Okay? And this is like incredibly fictionalized. It's height and weight. Okay? And we've plotted apparently, a normalization, some very heavy cats and some, very light elephants, I guess here, small elephants. Okay? But the idea here is that there's a bunch of cats, which are these circles that are orange, and there's a bunch of elephants, which are those gray, squares over there. And this is our data. We want to model and do this. All right. Now, the point I was just making is that in the discriminative case, so far we've used a lot of lines, linear models, to do this. You could use something else too. We saw how to make something that was nonlinear look more like a line. But we would basically come up with a decision boundary. And intuitively, this makes sense. If you imagine there's all kinds of weird subpopulations of elephants up into the right corner and cats to the left corner, and we didn't have to learn any of those. We just learned when a cat and an elephant are close, how do I tell them apart? Now, when I say that out loud, that sounds pretty ridiculous, like a cat and elephant are close, but hopefully you get what I mean. If you have two classes that are difficult to distinguish, you're kind of devoting all your horsepower right to that decision boundary. So both of the classes enter into it. But that's not the only way to do this, right? In the generative approach, what we're going to do, instead of finding that boundary, is we're going to model each class effectively independently. Okay? We'll come back to what we actually relax in practice. But we're going to ask instead, what do the features look like for every class? So is there something about an elephant that is dramatically different than a cat? Maybe it has a trunk, or, whatever you think about, okay? And then we'll also try and learn how likely each class is. Okay, so the prior distribution. And why do we need both? Well, if you think about this, we're going to probably do classification with Bayes' rule. Okay, so let's look at what this looks like in the example. All right, here's the generative idea in pictures. So if you look, what we're going to do intuitively in this classification paradigm is we're going to learn one model, which are these gray circles, these ellipses that are over here. We'll come back to those if you don't remember. Those are going to be effectively Gaussians, if you like. And this white thing. And then we're going to learn something in the orange. And we're going to kind of learn their center of mass. And then in this very simple generative model, we're just going to learn their distribution. So basically what we've learned here is, cats are smaller and way less, elephants way more, and they have some variance. And we're going to make the variance fixed for the point of view of the slides. We'll come back to that later, okay? Or their covariance. And I'm going to talk about what covariance is, if you're not familiar with it, in just a couple slides. And this kind of visualization will make more precise sense. But at this stage, all I want you to think about is really what we're going to do is somehow we're going to create a model. And the intent of the model is, look at all the cats, build a model. Look at all the elephants, build a model. And then we're going to classify a new data point, say this green point, how? By looking at how likely it is under model A and how likely it is under model B. So if that p-value is higher, if you like, that probability value is higher under the elephant model, we're likely to say that with some probability it's an elephant. So far, so good? And how we decide that is Bayes' rule, right, which we've done several times in this course, and I just skipped over. At this level of abstraction, everything clear? All right, awesome. Please go ahead. Ask me questions too. All right. Okay, so this is the plan, just recapped. Find a distribution for cats. Find a distribution for the elephants. When a new animal comes in, does it look more like a cat or an elephant? At a high level makes sense what we're doing and mathematically what's going on? Okay? Now, I will say in the way we apply generative models, like in GPT, the difference is we devote a lot of horsepower to trying to learn how to generate text, okay, in that generative way. We try and learn very complicated representations. For the point of view of this lecture, GDA, we're going to take about the simplest version that we can get of a model that's still useful. And surprisingly, even though this model is very simple, we'll see that you can build pretty reasonable things out of it. And that's our plan for lecture. Okay. All right. All right, so we have to do a little bit of a detour. These are the new Claude Matplotlib generated graphics. Let's see how we did. All right, so recall the one-dimensional Gaussian. Remember that it's written with this notation here. This means Z is drawn according to a normal distribution. This mu is the mean. I'm just write that on there. So helpful. We call this character the mean. I'm sure you recall that. We've been using it a lot. And this guy the variance. Okay, I'm not going to write that. All right, get back to here. All right, that has this distribution function here, which we've seen. Z minus u squared, mu squared over 2 sigma squared. All the normalization that we've typically done. This is the normalizing constant. All right, so what I've charted here are a bunch of different values for sigma and how they affect what's going on. When sigma is small, it gets very, very spiky, right? Intuitively makes sense. If you have low variance, you're very concentrated across your mean. The heights are different. Why are the heights different? Exactly right. It has to integrate to 1. Exactly perfect. You have 0.5, you have 1, you have 2, and you're spreading that mass. And the integral underneath is normalized to 1. All good. All right. All right. So let's imagine our fictitious example with the cats and elephants. Let's imagine we're just looking at their weight. Of course, this is like, who knows what units are in here. That's like me copping out. I mean, I don't know what axis you can put cats and elephants on the same weight. Maybe they're very large cats or very small elephants. Who knows? Doesn't really matter. You get the point, okay? The point is in this alternate universe with cats and elephants, cats are lighter and elephants are heavier. And what that corresponds to is, of course, the mean of the cat is lower than the mean of the elephant. Okay. All right. So now how do we do this? Well, we have this probability distribution function, this kind of likelihood function, and we can compare these two values when we get our new point here. So we have our new point, which is our new animal. We're unsure if it's an elephant or a cat. I guess it's possible that a cat is that big, but it's very unlikely. But this is like a pretty reasonable size for a small elephant. So far, so good? All right. All right. All right. We'll go into this in a second. All right. Okay, but what happens when we generalize that simple example to 2 dimensions? There we need a little bit more notation. We haven't really had multidimensional Gaussians in the class, but they work hopefully like you would expect them to work. So we have an x, which is going to be in Rn. This n is going to be 2 in our example. That's the dimensions, but it could be higher. Okay. We write x is distributed according to mu and sigma to mean the following. Mu is the mean vector. That's going to be the center. If you think back to the elephant diagram, these were the stars that I was drawing. These were the middles, the means, the average mass of what was going on. And then sigma is going to be this covariance matrix. And if you remember, that means that it's going to be symmetric. Okay. So the entries across from each other are the same in the obvious way. It's positive definite. Okay. It means it has, what does a positive definite mean?
You transform the A to use all the greater zeros.
Yeah, that's a great definition. So you gave me, wonderful. So the definition here is that has to do with if you take a vector and you dot it through sigma, you say sigma transpose sigma z, that's always going to be greater than or equal to 0 if it's positive semi-definite. And that's a function of the fact that its eigenvalues have a particular structure.
In this case, it's positive definite, so the ellipse is not flat.
That's right. That's a great consequence. The statement was, because it's positive definite, the ellipse is not flat. That means that they actually have round values. There's no 0 variance in any dimension. Please. Fantastic. That was the one I was looking for. The eigenvalues are all positive. It has eigenvalues because the matrix is symmetric. Not all matrices have these in a way that makes sense, but that's because these two things basically tell us that we can do all kinds of nice eigenvalue things. That will be the consequence. That fact will be used, actually not so much today, but in general about these matrices again and again. Okay, and this is the analog, by the way, of the variance being positive, right, or non-negative. 0 variance means you're certain in that attribute. Okay, cool. All right, that also means I can write this. I can take the inverse. Because it has all positive eigenvalues, I can factor it however you like, eigenvalue decomposition, invert the eigenvalues, take transposes. Okay? It has that property. All right? So in particular, that allows me to write this, and life is good. If it did not have that property, if it had zeros, I'd be in trouble, right? The zeros would kill me in both places. This wouldn't be defined. This is the determinant, right? So remember this expression here. This is the determinant, square root of the determinant. If that were a negative number, I would be in trouble. Determinant is the product of all the eigenvalues. The product of a bunch of positive numbers is positive. So I'm taking a square root, so that's important there. And then here, if there were a 0, well, this would no longer be well defined, and I'll think about that like a distance. Now you can get around that if you really cared about the 0, but the negative stuff would cause you problems. Sound good? All right. Okay, you don't have to know this name, but this basically you can regard as a distance function that is weighted by those eigenvalues. If this is unfamiliar to you, these use of eigenvalues, it won't be so bad today, but I'm warning you in the future that I'm going to use these quite aggressively. I think next week you get Tengyu. Isn't that a treat for all of you? And then the week after that, you get me back for a week, and in that week, there will be a lot of eigenvalues. It's like eigenvalue week, okay? That's going to be everywhere. So I just want to highlight that if it's unfamiliar. And this is a distance in the sense that, like, it satisfies the properties of a distance, so that, it's just scaled in a way. All right. So far, so good? Everyone understand all the definitions? Let's look at some pictures, make sure they sink in. All right, this is where Claude really outdid itself, okay? I used to draw these, and there was a lot of gesturing, so we're cutting all that down. Now we have Matplotlib, like 1980s technology, to draw for you. Maybe 1990s technology. Anyway, this is what a 2D curve looks like. Instead of the bell curve, it looks like this and symmetric in all directions. Has this nice little cone, little circle in the middle. It's a surface and a contour. I prefer not to do this. I'm going to show you the contour version. This is one variant where the height in 3D tells you the value of P. Okay? And this is now in 2 dimensions, x1 and x2. Okay? This is the standard Gaussian. That means it's going to have a covariance function, which is the identity. Okay? All right, cool. Effectively, it means every dimension is independent. Here's some more Gaussians. They have weirder shapes. So remember, in 1D, they could kind of only be like flat. They could be pointy. But now, when you have higher dimensions, you have more degrees of freedom. Okay? So these models get correspondingly richer. Here's one where you have sigma I. It's there. It's nice and round. If you make sigma diagonal, and those diagonal elements better be positive, right? Because of the properties that we just outlined. Then you're going to stretch each component in different ones. And I have to say, I'm not super impressed with what Claude did here because it looks kind of weird. But maybe I'll go back to my old ways of gesturing with my hands. That seems to be better. So imagine you have it axis aligned. So you have it diagonal. So the diagonal is 1 and 5. What's that going to look like? Well, I'm going to have 1 unit in this direction and 5 units in that way. And then I have the ellipse. Oh, look at that. Look at that drawing technology. Amazing. I don't need Claude. Anyway, I love Claude. No, I'm just kidding. That's all going to be recorded in transcripts, and they're going to download all of it, and they're going to know exactly how good or bad we were to the AI. So don't curse at it if you saw. Don't curse at it. Anyway, so back to this. All right. Every lecture should include one unhinged conspiracy theory. I think that's a requirement going forward. Anyway, it does actually monitor. Claude Code does monitor, right? If you curse at it, so you shouldn't do it. It's just like you should say please and thank you. In any case, just be a good person. I don't know what's wrong with me. Anyway, all right. So this is full sigma. So what happens if it's not diagonal, okay, but it's actually a full positive semi-definite matrix? Remember your linear algebra. What does that mean? It means its eigenvalues again have this stretch, but it's rotated the basis in some way. May have also flipped it, but that's a separate issue. Okay? Does that make sense? Remember what orthogonal orthonormal transformations do? That's all it can do. Okay? So it do it and all the rest. The center is given by the mean. There's this rotating behavior and this scaling behavior. And that's what Gaussians do. Okay? Pretty rich structures, especially in really, really high dimensions. All right. All right. This is, animation to say what I just said. Tilted, diagonal, so on. Okay. All right. I actually prefer, rather than that fancy 3D version as I drew to you, when I have to fall back on explaining things, I prefer this contour version. Okay. And this is kind of like the version if you were to go left to right in 1D, where you would start to say, how many sigma out are you? These lines here, these contours, these are level sets. Okay. So all of them have the same value for P, the probability. That's what it means. That's what I mean by level set. If it's identity, then the level sets move at exactly the same rate. Okay. And I'm sampling them at some rate here. Maybe it's 1. Okay. In this case, when I have the diagonal 3 and 0.5, getting back to the earlier piece, it's axis aligned. That means that it's the axis that it's getting stretched or along those axes. It's getting stretched, 0.5 and 3 in this direction. Okay? So far, so good? All right. Here's positive correlation, and here's the whole thing. Shifted together in negative correlation. Okay? Just does a shift and puts it in there. All right. We're in good shape. Okay. All right, so we talked about the axis-aligned ellipses. We talked about the rotated ellipses. And yeah, we're in good shape. Okay? Entries can be, oh, that's one thing I want to say, sorry. Entries can be negative, but the eigenvalues are positive. Okay? Positive eigenvalues do not mean that all the entries are positive. People get confused. All right. Controls the shape, size, and orientation of the Gaussian contours. Please.
All the diagonal entries have to be nothing.
Right. So, yeah. So in particular, when you have a diagonal matrix, because those are the products of the eigenvalues, you do have to do it. And even individually, they are the variance of that individual element, which will also be non-negative. So they will be positive in these kind of matrices. One test that you can kind of think about is diagonal dominance. So this is a quick way, if you were like looking at a matrix to tell, which is if you look at the entries and all the other entries are smaller than the square of that entry, then you're looking at a positive definite matrix. Yeah. Wonderful question. You guys got this perfectly. Okay. Awesome. But already in 2, we're starting to see positive versus negative correlation, which refers to the off-diagonal entries. Okay. Can't really define that when you get above 2 because, you get these kind of pairs. Okay. Actually, there's one lecture which I'm not going to give, but I will just tell you one piece about it. The inverse of these matrices, and especially the inverse of Gaussian matrices, have all kinds of interesting structure. In particular, if you invert a matrix, I'll just leave this as a challenge problem. Maybe I can write up how you prove it. It turns out if there are zeros in the inverse, that actually means that 2 variables are independent. Okay? It's interesting thing. Neither here nor there. The actual covariance matrix doesn't have that information. The inverse does. That's why the inverse is in the formula. You can just write out what I'm saying from that. Anyway, this is like what, if you take graphical models, this is basically what it's using. It's called Clifford-Hammersley theory. Doesn't matter for now. Anyway, but it's useful. Useful to know. Okay, so changing mu shifts the center, and the shape stays the same. Okay. All right. So what we're going to do right now, please.
Inverse covariance matrix has information about whether or not 2 variables are independent?
Oh, it's easiest to read in that matrix. Yeah, great question. So it's not that it's only there. Clearly, information is summarized both in the mean and the covariance, but it's actually transparent. And this is maybe a throwaway comment that I shouldn't have made and just kept to myself. So apologies, but I'll explain it. If you take the inverse and you look where xi and xj are independent, the inverse entry will be 0. And this is a very famous theorem from stats from like the late 70s, which gave rise to things called graphical models, where you write down which things are independent and which are conditionally independent. And this is just a beautiful bit of structure that happens to be lurking in Gaussian random models, which in a past life I studied. So I felt I had to vomit that out for you. Sorry.
So it's
the covariance itself does not give you that information nearly as readily. So if you look at that information, it's very difficult to say because independence requires a factorization, but the values can be non-zero. But here, once you normalize appropriately, you get 0 entries in there. And this is actually very useful when you're looking at data sources to decide, are they approximately independent? If you look at their inverse covariance matrix, this is actually a pretty reasonable test, which is a lecture that I gave last year or 2 years ago, but shelved this year. So we could make more deep learning, which is more important. Cool. Awesome. That is just for your interest. This is not stuff you need to know. Okay. All right. Back to GDA. There's a different mean with the same covariance. Now, you could say, what if we have different covariances? We'll come back to that later. You don't need to know that. But right now, we're thinking we just have different means, and we want to do this. So we want to find mu of elephant and mu of cat. Okay? But we're going to keep the spread and shape the same. Okay? All right. Let's do it. The GDA model. Okay. So, given training data, xi and yi, like before, I lives in RD, yi lives in 0, 1. We're going to assume as follows. We have y is going to be a class prior. This is our model of how we think about generating the data. How likely are cats versus elephants? If we have, many, many elephants and a tiny number of cats, or the other way around, we would encode that in this Bernoulli right here. That would be the weight that they would come out. Then the idea is, intuitively, for the cats, which I'm making 0, We then draw according to the mu0 for the cats. So the cats are mu0 in this example, and they both have this fixed covariance. So they're drawing against that random model. This is kind of how the data, as you know, as we talked about, we hypothesize a forward model, and then we invert it. And perhaps not surprisingly, this is the distribution for the elephant features. It has, the big difference is right here. They have different means. We wanted to wiggle the smallest amount possible. Okay? That's pedagogical, not necessary. That's what GDA does. Okay. So the takeaway assumption is the two classes share the same covariance, but they have different means, and now we want to find those means from data. Okay, so let's write out the distributions. So here's the class prior, okay? It says we're in the class with probability phi, and we're in the other class with 1 minus phi, because it's Bernoulli. Here are the class conditional densities, right? This is the next phase. This is, say, for example, the cat. Why do I know it's the cat? Well, it's y given 0. And then I have mu0, mu0. Everything else is going to be the same when I look at the elephant in a second. So far, so good? Please.
I remember the image you had of like the yellow circles and like the green circles. So if you have the same covariance matrix, you're saying those are like, they have to be the same shape.
Yeah, exactly right. Let me go back to that for 1 second, just so I can show it to you. How do I do this? Okay. Oh, I know why it's not working. Got it. It's 121. This is it. Okay. So what I'm saying here, this diagram did it implicitly. These contours and these contours are meant to be the same. Okay? Because the covariance is the same. So both their orientation, how they're rotated, and the strength, the size of the principal and the other axes are the same for both of them. And what we're trying to find are just these 2 point star, the orange star and the gray star.
But what if like the data for the elephants and the cats would be like
Awesome question. So the question is, this seems like a ridiculous assumption. I know you didn't say that, but it's fine. This seems like a ridiculous assumption. Like, clearly the elephants have different variants than the cats. And I would say, you're right. But it's a question for what are we modeling in this exercise? And right now we're modeling that they have about the same variance. There exists some variance that we're going to fit that's the same across both, which we're going to use. And you'll see how this falls out in the distance. We'll see in a little bit, exactly for the reason you just asked. What if I want to have different covariance? It's going to require a couple of extra lines that we put into the estimation procedure that we have. And so yes, you could model that, but it's a modeling choice. You may decide it's not worth it. And by the way, fitting the covariance is not cheap. It's got a lot of parameters, right? If you have a really high dimensional feature vector, like, D is very, very large, then the covariance is D squared. Now it's like D choose 2 over 1 because this is the symmetry assumption, right? You don't have to do things below the diagonal. But that's still a lot more parameters. And the question is it worth it? And in many applications, the answer is maybe not. And so we're going to start with this one first. Wonderful question. Okay. All right, we're back here. Okay. All right. These are phenomenal questions. Please keep them coming. All right. Now, notice that because of this kind of cooking show and was highlighted that we're only changing this one mean, all that's changed are the entries of mu here, the means. But otherwise, these two distributions look the same. The other way they're asymmetric is this. We allow to have many more cats and many more elephants. Let's imagine you had a data set. Why would that happen intuitively? Let's imagine you have a data set where you have 1 million cats and 1 elephant. Okay? That was what you saw. The ratio is 1,000,000 to 1. So intuitively, if it's on the border between the elephant size and the cat size, you're probably going to think it's a cat because you're like, oh, there's almost always cats. If it's even, remotely unlikely, that weighting between the two things will come out through Bayes' rule. Okay? And so pay attention to that. So that's the one kind of non-trivial thing that's happening here. Or I say the two non-trivial things are the means are different and we allow the population sizes to be different. And that's the whole model. Please.
Bayes' rule, you have to assume that the training data has the same ratio as the mistake.
Awesome question. Yeah, so the question is, do you assume if you're using Bayes' rule implicitly that this now is a higher assumption? So what are we assuming carries over? And we're really making some pretty strong assumptions here in terms of what carries over. But again, remember, they're not true or false. They're like, how bad are they? They're always going to be bad, but how bad are they? So if, for example, we trained on a very skewed data set where we have that million cats and that one elephant, and then at test time, we're shown cats and elephants from a population that are effectively the same, we're going to make errors, right? We're going to make some class of errors when we get those elephants and cats that, we're going to always assign in this example, or more frequently assign them to the cat class, when honestly, we should have been more open-minded that they're just really small elephants, okay? That can definitely happen. The other here is we have to assume that the means that we observe are somehow concentrating. There's a fancy word that basically means that what we're assuming in the distribution is we've seen enough to estimate these parameters appropriately. That means that like our model, for example, even if it were shown a billion more elephants, it doesn't have the resolution potentially to move the center too much. It's not going to make too much of a difference. So the other implicit assumption in there is how much data do we have to actually learn from? And then to what extent does it carry over? But those are the things that we're assuming. We assume that the training and test data sets are representative in that way. Wonderful points. Those are exactly the right questions to ask. What am I assuming about my train to test time? And then what capacity of model am I using? And why am I doing that? Right? These are like the absolute core questions of machine learning. Awesome. More questions? Please.
There are maybe more cats than there are elephants. That's how we train.
It could, right? So the question is where does that come up here? It comes up effectively in this class probability. So if you imagine, so the question is, what if there are a lot more cats? If there are a lot more cats, as we said, we're going to come out with a probability that we're in class. Our prior distribution that's in the class is just going to be a lot harder. That means intuitively, we should expect to have to take more evidence, all things being equal, that we're going to conclude a given point is an elephant. And although Bayes' rule, I think, when you kind of learn this stuff, feels like some mechanically strange rule, that's the magic that it's doing. It's telling you how to weight those two evidence pieces in a, Bayesian optimal way. Too much words. Just in a fine way. Okay, it's a rule to do it. Perfect. Good questions. Others? Fantastic, folks. All right, let's keep going. All right. Oh, I should have just scrolled to the next chart. I'm sorry. That was my mistake. You were asking about this question. I was right here. All right. So this is what we're trying to do. We're trying to get mu0, the cats, this character, mu1, the elephants, this character, and just get the means. I raised a bunch of issues about this, so I'm not going to go through it again, but please feel free to do it. The fact that they're shared covariance means that, you could cut and paste and recolor these ellipses that are around each of the means. Cool. All right. So we need to learn these four things. The class prior. What fraction are elephants? And implicitly, what fraction are cats, since we only have two classes. mu0, the mean of the cat features. mu1, the mean of the elephant features, and sigma, their shared covariance matrix. Okay. Now, compare this with logistic regression. Here, we had only these d+1 features. GDA models much, much more structure, and we're paying for that structure, as I alluded to earlier. We were finding the means of each of these classes. Okay, those are like not very different. Those are like the thetas we had from before, roughly, right? They're about the same. They are the same size and shape. Maybe differ by 1 because we don't have the +1. And we're also going to get this covariance matrix. Why do we need? I don't know what I just did. Took a picture. I want to remember this moment forever, I guess. What the heck? All right, good. I didn't even know I didn't know what gesture that is. So if we do that again, we'll all be surprised and excited. All right. Okay. So this covariance, why do we need that intuitively? Why can't we just use the means?
It's like the rejection is parameterized by the mean vector and covariance to get the shape.
Exactly right. The point is, you can't get the shape to get a distribution. You have to, when you have 2 points that are there, like your two means, you want to have some way of a point in the middle being able to assign the, probability to it so we can run our probabilistic estimate. You could just take a distance, a flat distance. That would kind of like be what you would do if you did the identity function. But since we want this probabilistic interpretation, that identity function is just a standard Gaussian. Okay? That's what it kind of boils down to. We want it to normalize, we want it to tail off, we want it to be bounded, all the rest. We don't have to decide, like the Gaussian doesn't make us decide that it only works in a fixed range, right? Like you could say, I only want a distribution over distances 0 to 5, all kinds of weird things. The Gaussian is just kind of nice and simple, but it lets us then still have a valid probability distribution. Okay. All right. That was a potentially low-class segue into maximum likelihood. The reason we needed the sigmas and all the rest is so we could have likelihood functions and run the probabilistic machinery. All right. All right. Here's that probabilistic machinery. You've seen this before. All right. Given data, xi, yi, we're going to write a joint likelihood function. Here's our likelihood function. What is it doing? It's taking all the parameters that are in there and it's scoring them in some way, according to that model. And I've been a little bit remiss here. I didn't write all the semicolons with all the parameters on the side. I warned you about this in advance, but be aware, these probabilities are with respect to these parameters. Okay? All right. Now, why were we able to write them as a product? The IID assumption did a lot of work for us right there. Okay? Second one, we did this factorization. Well, this is Bayes' rule. Okay? We can do that every time on a term. We didn't have to assume anything. Okay. So we're going to model the joint distribution P of xy, not just P of yx. Okay? There is, just as an aside, if you look up in the literature, there are things called energy models, which do model this directly, especially for things like diffusion, which is a really popular form of generative models, which we love here at Stanford. And in general, people love them. They make great images and eventually text as well. But this is why it's different. You're modeling the whole world. Okay? And the kind of example I would use is if you trained, actually, I'm not going to give you a confusing example now, but Px of y is actually modeling the world. You want to model how likely the data are and how likely the labels are together. Okay, that's roughly what we're after here. Not modeling just the conditional distribution. Okay. Okay, so let's do some arithmetic. That's some very basic stuff. Okay, so we're going to take logs, not surprising. Why do we take logs? Because linearity, and we turn them into sums. We now have these log likelihoods, which we needed everything to be positive on them, so they assign something, which again makes Gaussians nice because they never go identically to 0, so we can do this. Boom, boom. Okay, this is our prior distribution. Okay, so we're going to do the standard thing. So we could solve this with gradient descent. No reason why not. But something magical happens. And something magical happens is we can set the derivatives to 0 and solve it and get a closed form solution. Okay. This isn't necessary for Gaussian models, but GDA does have this nice feature. And that is a feature worth pointing out because often people would use these generative models in situations when they wanted to compute something relatively cheaply. And we'll see probably the archetype of this, something called naive Bayes at the end of this lecture, which is a very good first model. It's a count-based model. It's a very nice model that you can use, and it's dirt cheap to build and evaluate. Okay. So let's find those closed form solutions. All right. Here's the class prior. So, let me see. Oops. So how do we estimate the class prior? We just count. That's it. You can look. This is exactly the maximum likelihood estimate. You'll see later that sometimes we'll do a very sophisticated trick. It has a fancy name. Laplace priors. Does anyone know what Laplace priors? Show of hands. Yeah. You add 1. That's what you do. Okay. You add in synthetic counts. Okay. All right. What are our class means? What would you expect them to be? This fancy notation here, again, this 1, just to make sure it's clear, this says this only fires, it's 1 if the point is equal to 0, and 0 otherwise. So this just adds up all of the x's in class 0. And then it divides by the count of the number. So this is the count in class 0. Ooh, and it'll disappear. Okay? So, and that's their mean. This is a most obfuscated way you've ever seen to compute the average. Okay? That's what we're doing. Take all the points, add them up, divide them. All the cats. These are all the elephants. Clear enough in the notation? Okay. All right. We didn't have to compute any gradient descent to do this. We just had to add it up. Again, nice feature. Okay, average vectors. All right, so far so good? Everybody's happy with this? Any questions about it? Now, we're going to estimate the shared covariance, those circles, and that's going to let us do a little bit of matrix stuff. And if the matrix stuff isn't familiar to you, go to the Friday things, look at them. Okay, so here's the shared covariance, sigma. Okay, this is xi minus the mu of that class that is appropriate to it. So like for every data point, we look at its label and we pick the appropriate mean. Okay? We're pooling all the data together. Okay? Perfect. That's what that notation means. Okay? This character here. Please.
For the estimated covariance, you're assuming that
For right now, we're going to assume because we computed them on the last slide that we have access to them. Because those means, there's no circularity. So the question is are we assuming we have the means and we got them, we estimated them from the last slide? You're right that I'm cheating in some way, which I don't know if you're pointing out, but I would really, if you are, it's wonderful, which is that the actual mean, the true population mean, we're only seeing a noisy version of it. So there's some error in our mean, right? Which we could compute how quickly it goes to zero and all the rest of that, convergence rates. I'm skipping all of that. Artfully, shall we say, for the moment. So for the moment, I'm assuming I have it exactly to make my life a little bit easier. But you could do a plug-in estimator for this. It won't be too bad. Great question. Really phenomenal question. Please. Awesome question. So this question that you asked, I wish I brought candy today. I'll give you extra candy. This question is like one of my favorite questions. So in what sense are we learning this thing if we're not doing gradient descent? And this is one of the things that's interesting to me. Learning is about this kind of inference against the maximum likelihood in this framework that we're doing. The fact that we can solve it in one step is, doesn't negate its ability to learn. It is doing a form of learning. In fact, you could solve everything we've done here with gradient descent. It would just be a lot less efficient than plugging in the answer. Okay. And so that difference of why is this learning is kind of an interesting thing. Now, in general, we'll see that we don't know how to learn without these more expensive procedures. But that is I had a lab meeting last week where we were talking about different procedures that are not gradient descent-like to estimate some of these parameters. And I think even Hebbian learning, which is another parameter, came up. They're all still forms of learning because you're still trying to understand from data how to make future predictions. Yeah, great question. Others? Cool. We can make it more complicated in a sense. When we make it more complicated, then we will have to use gradient descent. Okay. All right, so how do we actually derive this in the log likelihood? This is the proof. So what I did, and the last thing is I gave you this intuitive version. This is the proof. I'm going to go through it relatively quickly of why mu1 is what I claimed it to be. The idea here is that this is the term in that log likelihood that we cared about. If you remember, there was also a class prior, but when we compute this derivative, it's going to fall away. It doesn't depend on the mean. So this is the only term that actually depends on the mean. So if that makes you feel uncomfortable, where did it come from? It was because I had the logs that were separated, and that term I knew was going to go to zero. So I used this notation to hide it. Okay. All right. When I do compute this derivative, notice that I get this expression here. Okay? Verify that when I compute the means on each side, because it's a quadratic form, it's going to get one side and the other and transpose. So I'm just going to get this is going to cancel just like a quadratic, and I get this. Now, the interesting thing about that is, if I look here, this inverse plays an interesting role. What does that tell me? So the only way, since the inverse is on there, I'm not sure if I write it out like this. So since this is invertible, I can pull this out by linearity, okay, on the entire thing. It makes the notation a little bit nastier. But if this invertible matrix is multiplied by something and it equals zero, what do we know about x? So if ax equals 0 and a is full rank, what does x have to be? 0. Exactly right. You got it exactly right. And so that lets me conclude that, in fact, this is true. Okay? That's basically saying I don't have to worry too much about that. If sigma were not invertible, what would go wrong in that reasoning? Please.
Space, so it's not necessarily zero.
Fantastic. The vector here could be in the null space, so it wouldn't exactly be 0. We could only conclude, for example, that xi equals the mu up to some extra term. It wouldn't be identifiable. This gets back to the why are we doing this kind of assumption earlier. Okay? Awesome. So there'd be an entire one dimension where we couldn't tell where the mu lived, if you like, roughly speaking. Okay, cool. And then this is just more of that terrible notation thrown to compute the world's most complicated average. Sound good? All right, so this justifies it though, okay? So why did I do this? Again, so one very grim way to look at this slide is, this is the world's most complicated derivation of computing the world's most complicated average, in which case, like, you know, good for me. But actually the reason we're doing it this way is that this technique of going from likelihood to parameter, this is a simple case where we should sort of be able to intuit the answer. We're going to do again and again. As we get to more complicated models, we're going to compute these derivatives on the population. We're going to solve these things, and you're going to have to do that in homeworks and other stuff coming up. Okay? All right. So this is not a surprising thing. Okay. All right. And you can do all of them. You can do the mu's, you can do the sigmas, you can do it all this way. All right. Now, this is a little bit of extra stuff that I wanted to throw in, just because I wanted to talk about this decision boundary a little bit. Okay? So part of this is standard. Part of this, there's one figure that's not. So when you have a new animal, how do you do the prediction? Okay? So you take this argmax y hat, take this argmax over all p of x given y. Okay? So this means what you're going to do is you're going to take all the labels and you're going to say, given the data that you've shown me, I think it's very likely that it's an elephant. I think it's less likely that it's a cat. If I had more examples, I would do more examples, but right now we're doing binary classification. Okay? And I just compare those two and take that argmax, and indeed I get this little function here by Bayes rules, and I notice, actually, p of x doesn't depend on y directly, or shouldn't depend on this directly, so I get this kind of argmax. Okay? This is where the population comes in. This should be, doesn't depend on x, sorry. I'll blame Claude, but it's probably me. Okay? This term goes away. That's what I'm arguing. This is wrong. Okay? Clearly it depends on the label, right? Like more cats, you're going to be more likely to say there's a cat. Okay, so this is where the decision boundary comes up. Now, what we're going to do is we're going to write out these probability distributions here and try and figure out exactly where the probability that we decide we flip from dog to cat. Or, we're doing cats and elephants, okay? Got to keep it straight. It's super important we know which animals we're talking about. Anyway, so we're going to take the logs and we're going to expand the Gaussians and look at these terms. And what we're trying to say is where are they equal, right? Because we assume they're monotone decreasing inside, right? Because of the way the Gaussians look, right? They're monotone decreasing as it goes away from you, right? What's happening? And so we're trying to find that decision boundary. And we're going to try and find all the places where they give exactly the same probability. And that probability is a function of all this good stuff. It's a function of the Gaussian. It's a function of the class prior, everything else. So when we expand, because we did this trick here that sigma is shared, we're going to be able to cross out a bunch of terms that involve sigma and all the things that are, on sigma xtx kind of terms. And that's going to leave us with this piece. Maybe I didn't draw it. Did I draw it out? Yeah. Okay. So it's going to, these quadratic terms, they're all going to basically go away. And I'm going to get a bunch of cross terms and other things based on the mu. The mu terms are all going to be constants, right? So when I take this term and put it through sigma, it's just going to give me some constant, right? That's the inner product. It's going to be bigger than 0. And I put that in. And the point is that this gives me a totally affine term. Only linear terms suffice in x because this term cancels because it's shared. Does that make sense? I gave a terrible explanation, so it really shouldn't, but hopefully you're smart enough and kind enough that you're got it. All right, good enough. All right? The point I'm trying to make is the decision surface is linear for GDA when sigma is shared because this term cancels. Okay? All the quadratic terms go away. You equate everything else. So here's that term. So this is the form of a hyperplane. And this is the actual odds. This is the log odds. The offset is exactly the log odds. We get all the differences between the means, the plus and the minus. You can compute all of this. So it basically says this is the expansion that we're going to get. And so after all of our work, we got a line between the two of them, which I told you we were trying to avoid. But what happened here? Okay, so two things that I want to point out. One is, conceptually, we modeled something quite different. And I'm going to show you that actually our conceptual modeling can give different decision surfaces. So give me that in 1 second. I'm also going to show you one other representative thing, which is this line here it will turn out that many of the generative models effectively give you the same discriminative line, and that discriminative line is given to you by logistic regression, which is a super interesting point because we had to assume a lot of things to cough this guy out, this generative model, right? We had to assume, the covariances were shared. We had to estimate all those parameters. Now, they were cheap to estimate, so that was good. But it ended up, we got to a decision surface. So I want to go through each of those points. Any questions before I move on? Is it clear how we derive this? The most important takeaway is GDA in its current form does have a decision boundary, which is a line, even though it does all this nice, good probabilistic stuff underneath the covers. Please.
You showed the cost terms of zero with the...
Oh, sure.
Can you explain that again?
Yeah, so the thing that I glossed over, which was a little bit strange, is this term is going to cancel. So when I expand x here, let me write it out. Maybe I'll make a huge mess of this, so apologies in advance. Maybe I'll write it in blue. Okay, when I expand this term out, I'm going to get x transpose sigma inverse x on this side, plus a bunch of other things, like minus mu transpose sigma inverse x. Let's see, what else will I get? I will get x, I'll get the other one, x transpose sigma inverse mu1. This is all this term here. And then I will also get plus mu1 transpose sigma inverse mu1. Okay? This term is a constant. Why is it a constant? Because mu1 is a constant. Sigma is something that we know. And so this will basically just be a scalar value. Okay? That's all it's going to do because we're dotting into each other. This term here has an x in it. It's going to vary with data. We're not going to cross that term off. And in fact, if you look, because these things are symmetric, these two terms are just going to give me, they're going to cancel with this 1/2 term that's in front. Okay? So this is the same term, just written in two different ways. Clear enough? It's that one's symmetric. They're both x dot mu via sigma inverse. Cool? All right. Now, this character. Well, this character is quadratic. We're going to come back to him in just one slide, but this character is quadratic. And the thing is it also shows up. I don't mean to say he's a he. I don't know why I called him he. But to me, he's a he. I don't know. I'm having a rough day. Anyway, so my point is this term also shows up on this side, and they will cancel for every x. And so the decision surface, this one is depending here on mu1, whereas this one's all depending on mu0. And so when I actually group all the terms, I get this nice expression that comes back right here. Okay? So when I go to do classification, this is what I'm getting. Okay? And so this forms a hyperplane. This is just saying that this vector dotted into x is equal to this expression, which is all effectively constants of the problem. I went over it way too quickly, so please ask questions. I'm super happy to slow down and parse this. Please.
Press roll that into x, or how did I expand?
Oh, how did this happen here?
Yeah.
Yeah, so this happened because when I went through this side, I'm going to get this term. I'm going to borrow this term on one side. I'm going to move it to the other side. And I'm going to have a bunch of the linear terms, which I'm also going to separate off in the mu1 and mu2 versions. That's going to give me the right-hand side. That's here. And the rest is just algebra. Like these guys moved over to this one. And I realized this was not a very good derivation because I was planning on trying to skip through it. And I appreciate you calling me out on it. I shouldn't have skipped through it. It is in Tengyu's notes or in the notes written out in full detail. But conceptually, it is just arithmetic. It is just doing a little bit of algebra to move things around and cross them out. And they are actually linear. The most important part I hope to get away from without actually having to do the computation, which was that this term cancels on both sides. And so everything else is linear or constant in x. That's the actual message of this, and that tells you the decision surface is itself linear. Because it's then going to be linear term or affine term equal to a constant. That is a line. Right? That's how you define a hyperplane. Cool. Awesome questions. Please.
So with classification, basically still works if you assume the populations have different covariance matrices, except that you'll get a different decision surface.
Yeah, wonderful question. So I'm going to come to that in one slide, or as I skip to the next slide, and we'll get right there. Wonderful question. Please.
Why does this relate to logistic regression? Like your hyperplane is like linear.
Wonderful question. So the question is, how does this relate to the logistic regression, and how does this change the decision surface? And both of those things are what we're going to come to in exactly the next slide. So give me 3 slides, and let's come back to them. These are phenomenal questions. They're exactly what's coming next. Yeah. Okay. So the intuition, by the way, is it's a line. There's some kind of exponential going on underneath the covers. We have a log linear model. Logistic regression is more powerful than you think for log linear models. That's kind of the punchline. It's not a sitcom. I can reveal that early. All right. Okay. So let's get to the first question. What happens if you don't have a shared? Oh, sorry.
Intuitively, the idea of having a linear decision boundary just means that I can divide up my data with this linear hyperplane to the point where I'm most confident that a point belongs to a certain class based off of where it falls on the decision boundary, right?
Right. So the decision boundary, this means, if you remember, we're going to do a decision rule. We're going to say, is this particular point more likely a cat or more likely an elephant? And we gave a rule to do that, which is consistent and that we can use, which is this Bayes rule that we ran through the model in a forward way. And so we got a score 0.6 for one, 0.2 for the other. And we got those probabilities and we compared them. And all we looked at to find this line is, when are those two probabilities equal? And we said that was the moment that we would flip, because we were doing this argmax. We would return the class boundary doing that. Now we threw away all that information with the probability model, which maybe we wanted, in which case this is a weird thing to do. But it was meant to highlight two things, which is, so far we haven't changed the decision surface from what we did last time. I'm going to show you that we can change it in 1 second. And then two, I want to relate it to this point about logistic regression, because there's a conceptual point underneath that will be more clear later. Wonderful question. Others? Awesome. All right. So here's the decision surface. And the point was made, which was a wonderful point. Well, I don't care. So what? I can still write out the decision surface. You just don't have to have the two sigmas cancel out. I can look at some other form there. It's just another quadratic form. I can solve that for 0. It's well-defined and all the rest. And you'd be right. And in particular, what happens is when that sigma term no longer cancels, you get these funny decision boundaries, because they're now quadratic. And that's kind of interesting because their shapes are different. So the left is the linear GDA when you have a decision boundary, and the right is called QDA, which is the quadratic discriminant analysis. And indeed, that's a totally reasonable thing to do. And you can do the entire derivation and how we estimated every piece. How would you estimate the means in this model? Well, you already know. You estimate the means. How would you estimate the covariances? Rather than pooling the data, you would do them separately. Everything kind of works out. But in this model, I want to point out, if Claude is to be believed and my checking of it is to be believed, these are decision surfaces. You should check that out. You shouldn't trust me or the AIs. All right. Good enough? All right.
Question.
Sure.
What does it mean that you have a situation where you could have a decision surface with no data points? What are examples?
Oh, we have no data points that are there? What a wonderful question. So the observation is, wait, there's this weird thing that's way out from the data set where all of a sudden it's making what looked to be in this setting a pretty unjustified leap because it doesn't have this monotonicity. What you'll see when you start to get to, decision surfaces that are more complicated, they will have these little knots, and we'll come back to exactly that point in classification. You're thinking about it in the same way. I would point out it's maybe more intuitive, but the same thing happens way off the map over here, right? Which is like when you get way, way out from the data, you're still using a linear model far from where you intended it to use. And so in the same way, when you're away from all of your data, bad things can happen. This one just looks a little bit more visually anomalous. Wonderful insight. All right. So now for the point about logistic regression, which we came to before. So what do these things have to do with one another? All right, so this is going to be a derivation. That's basically what it's going to show, is we're going to try and derive something that looks like the probability that y equals 1 given x, okay? The discriminative version of what we did. We've been doing kind of the other way around, right? We were trying to get to the other way around. So we want to go the other way around, over here, okay? So how do we get there? Okay, this is the discriminative one. Now, apparently Claude decided it didn't want to do the algebra. No. So there is some algebra that can be done. And the basic message though, maybe it's a homework problem, I don't remember. But either way, you can just see how to do it. It's hopefully not very challenging. Maybe you'll believe me and maybe you won't. And we'll all be richer for it. Anyway, so the point is you'll have this. You can rewrite this in Bayes rule. And that Bayes rule allows you to write this probability of y given x, which is the discriminative rule. And that discriminative rule has exactly this functional form. Now, what that means, it doesn't mean that it's exactly the same. It means that there is some logistic regressor that captures that decision surface. And so in a weak sense before, as you talked about, there's some line that given those features fits them. In some way, this is a tautology. I don't really need to prove it to you because I already showed that there was a line that we saw before, and clearly that decision line can be recognized by some kind of linear model, might as well be this one. What the content is that the probabilities on both sides are the same. And that also shouldn't be too much of a stretch, but you should go through it. All right. Okay, so basically GDA implies that logistic regression has the same, in the fancy terminology, posterior distribution has this sigmoidal form. Okay. Now it turns out, I won't prove this either, but it turns out that it's not just Gaussians. It's also other exponential families. Poissons, shared parameters, all the rest. And so it turns out that many different generative assumptions on your data lead to the same discriminative model, logistic regression. And it's not a coincidence. The reason it's not a coincidence is if your data fundamentally at the end when you do a classification rule is separated by a line, logistic regression is going to be able to basically represent it. Okay? And if it's an exponential model, the posterior is going to be of the form that it's going to scale as kind of a linear thing. And remember the way GLMs work, right? They had that term. They had those terms in the GLMs. All of them had this form where they would eventually be effectively logistic regression. Please.
So what makes a GBA model logistic regression is a linear decision boundary, or what is it that means?
Yeah, exactly right. So the question here is what links the two between the GLMs and logistic regression? It's the fact that they have two components. One is they have a linear decision boundary. And then the second is that they're in the class of exponential models. And that form, exponential form, if you looked at, always has a linear piece and then an extra term. That was the way GLMs work. And so all of them effectively are logistic regression in disguise. Now, the reason why that may be quite surprising is, on one hand, it seems like, why the heck are we doing all these different generative models if they end up in the same spot? And so one pro for logistic regression, as I talked about before, is although it's making a very weak assumption effectively about the data, this discriminative assumption that it can find some separator. It doesn't care how the data are generated at all. It's going to find that line, and it's going to get the probability close to that line in a good shape. On the other hand, what this kind of means is that if we're doing these kind of generative things, as we saw, you can get nonlinear decision boundaries, but you have to use extra and additional structure. So another way to say it is logistic regression became like the workhorse from data. So people really thought as a result of these results, like one thing that you would, if you were sitting in these seats 10 years ago, you're like, oh, I just need to know logistic regression. What's interesting is that a lot of the progress on AI and machine learning actually went in the other direction. So the two things that are potentially so strange is if you looked at stats was very interested in, just as a small digression, labeled data, proving generalization, and proving certificates. Machine learning was interested in subtly different things. It was interested in how you predict, how the predictions look. Didn't really care if you had the right values for the model. It looked about how to scale these things up, and so looked at these what are called over-complete representations. We'll talk about that later in the week. And all of these led to actually all the progress. And they were really worried about clean labeled data. And actually, we'll talk about, in 2 weeks, we'll talk about how to deal with unlabeled data. And it turned out that unlabeled generative data, like which were the quirks, if you like, even 10 years ago, are where almost all of the progress has been. The way that a GPT model works is it trains on huge amounts of unsupervised text during what's called pre-training. It tries to predict the next token, which brings a bunch of representations about it. It is a generative model underneath the covers, and it actually generates text, which is really what they mean when they say generative. Same idea. We scaled into regimes, as we'll see on Wednesday, which were like effectively, no-go zones for stats. We would look at models that had many more parameters than they had data points. So I just highlight this because this assumption right here is true. It's correct that these generative models can collapse to this discriminative model. Interestingly enough, the progress came on the generative side over the last 10 years, 10, 15 years, in industry and otherwise. All right. Cool. All right. Yeah, it's also, by the way, not true in the other direction. Logistic regression does not mean it's GDA. They are not equivalent models. GDA is making more assumptions. There are some decision surfaces that GDA won't be able to recognize. And the takeaway is logistic regression assumes less and still gets the right answer for these kinds of problems. And so I wanted to counterbalance that with, because you may think, well, if it does, I don't have to know the generative stuff. And I'll say, yeah, but then you would have given up on all this amazing AI richness over the last 10 years, which has been great. We've loved it. That's the way images are generated. That's the way text is generated. It's all generative stuff. All right. So logistic regression only assumes that the log odds is linear. And if you look, actually all exponential family models, if you look underneath the covers, that's really what they're doing. They all are these log linear models in their parameters. And in fact, that comes from another even more basic assumption, which I'm happy to share with you, which has to do with maximum entropy in the discrete case. But they all have to have that form. Okay? Cool. All right. Now, the traditional thing we would say is GDA needs stronger assumptions, but is more efficient when data is correct, and it's fragile if it's wrong. And logistic regression needs weaker assumption, but needs more data, but it's more robust. I would say this is a little bit misleading. This is the thing I'm supposed to tell you. It's like in the notes, all the rest. But it's a little bit misleading because of the story I just told you, which is it turned out that being able to model your data independent of class is a much more powerful idea over the last 10 years. Maybe that won't be true for the next 10 years, but at least recently it's been much more powerful about what to do and build interesting models. All right, so here are some examples of modern AI uses. Diffusion models, you iteratively denoise from Gaussians. You assume that you have, Gaussian noise. Like imagine I gave you an image, I noised it up with a series of adding Gaussian noise to it, and then I showed you the noisy model at the end. Could you go backwards, okay, from that and recover it? If you can do that model, what you can do is you can start with random noise that you pick appropriately and denoise it into images. And weirdly enough, that works. LLMs, large language models, these have generative things. GANs, probably no one knows what a GAN is. They are these generative and discriminator models that were really popular in like 2016. And they're still valuable, very cool models. But the takeaway is the probabilistic framework is the same. They model how the data is generated, then they use that model. And this is the simplest variant of this. And don't be worried that it doesn't do that well on linear kinds of problems. It shines much later, and that's why we teach it to you. Okay, so on that note, any questions on this part of the framework? That was a little bit kind of conceptual and weird, so I'm sure there are questions. Please fire away. That's a good way to get no questions, I guess. No questions? Awesome. We'll keep going. All right. So the next thing I want to show you, the last thing I want to show you is this naive Bayes model, which is a generative model for discrete features. So we're looking at things that were discrete. Oh, question. Thank you. Thank you so much for bailing me out there. Appreciate it.
I believe in one of the earlier slides, it said that sigma sub ij greater than 0 means positive correlation between I.
Sure.
Shouldn't that be with the inverse of?
Yeah, so that was in the specific case that they were 2D.
Oh,
Yeah. Great question. Please.
When you have the pro of GPA that wasn't on the slide that you mentioned, like why it's been so common?
Oh, yeah, great question. So the question was, why has GDA actually taken off in this? And at one level, I was just asserting the fact that generative models are the things that are potentially, the most exciting uses of machine learning over the last couple of years, generating text, generating images. In some ways, that's basically saying that this line of thinking led to them. The places where it's better or worse, I guess what I wanted to get across there is, it's very tempting when you take these kind of courses, we kind of put this very constrained box on you about how we're explaining their uses. And one use for machine learning is kind of the traditional statistics use. I want to take a bunch of data, I want to fit a model to it, and then I want to predict back. And so in statistics, you care a lot about, did I get the right parameters and all the rest. And what I want to say is one thing that I do like about machine learning and AI is that it's been fairly creative about how it's going to use the models. And so learning a large model to then go and generate a bunch of text is kind of an abhorrent thing to do by statistical standards, right? Like people ask questions like, well, how do you even know if it learns the same thing twice? And we're like, we don't know. But sometimes it generates cool text and pretty pictures. Like I remember once when there were these GANs and they first came out, there's a guy called Alyosha Efros, who's a professor at Berkeley, and we were having coffee. And he told me something, I don't know if it would mind me repeating this, but it was a wonderful thing. So we were looking at the first, they're called cycle GANs. He was a developer of these things called cycle GANs. And he was showing me these pretty pictures on his laptop. This is like what computer science nerds do. They're like, oh, let me show you my new model. So he showed me his new model. We're having coffee. And I was like, Alyosha, but how do you evaluate it? Like, it looks super cool. How are you evaluating it to try and hill climb it and do all these things? He said, Chris, my girlfriend, she makes pretty pictures and I love her. And this model, it also makes pretty pictures and I love it. And I was like, done. I'm good. That was the best explanation I've ever heard. So the reason I say that is these generative models, they have this feel that's a little bit squishy to get your head around. They're not just valuable because they do a better job predicting something, but they have all these other capabilities. And fundamentally, building models to understand how data are constructed has been an incredibly fruitful idea. Here it seems like kind of a stupid idea, like, oh, I fit the model and I just got a line out in the end. And so I kind of feel bad, like I'm doing you a disservice by saying like, it's better here and not better there. Like, who cares? I don't care. I don't care if you fit your linear models of GDA or logistic regression. But like, look how amazing the, LLMs and the, nano banana and everything is. Like, it's amazing. And that line of thinking of let's model the data led to it. That's all I wanted to get across. I just really love this stuff. So like, yeah, please.
Noises from the image.
Right.
How do you pick the noise image to get a specific image?
Oh, yeah, great question. So I think diffusion is actually later in the course. So I defer a full one to it, but it's much weirder than that. Okay. So actually the idea is that imagine you magically had a process that was reversible, that could take any image in the world and add noise to it, and then you got it through a chain of events. Now, imagine because you had that process and it existed, that you could somehow invert it and go backwards. Okay. Now, what I'm going to do instead of getting an image, because I want to generate a novel images, I'm going to pick a random spot in the space that's just noisy. And I'm going to run that same process as if the real image had been noised to this spot conceptually. And with that, I will generate a high quality, high resolution image. And so originally, like that is the idea. And so it turns out the math underneath it, almost no one actually uses the real math. Underneath it are these things, stochastic differential equations. I wrote a whole thing about it. But like, no one uses that stuff, honestly. They use tricks now to get it to work. But that's the beautiful idea that has been most valuable under diffusion. That's how like stable diffusion works. If you know what stable diffusion is from way, way back, maybe 5-6 years ago. And many of the new image generation models are like that. There are also text diffusion models that people have done. Stefano has a wonderful thing, and Volo and Aaron Liu wrote this wonderful paper a couple of years trying to get text diffusion to work, which has some really nice properties in code, which is super cool thing as well. You can also do it in any other environment. Yeah. You do not need to know about diffusion for this. Yeah, please.
Anybody try to use LLMs as like a discriminator model, like spatial?
Yeah, I think the thing is like you implicitly do, but you can do like such more powerful things. Like you can, for example, have it write a piece of code that does a test, which is something you can't really imagine a logistic regressor doing. I guess there's some way to screen out to do it, but the generative use cases tend to be more like write something to do it rather than use it. Now, when they first came out, this is a little bit by way of history, there were models that preceded the GPT models called BERT models. They were all named after, there's BERT and Elmo and all the rest, okay? And the first BERT models, they were these pre-trained models that are underneath the covers, and then people would run their sentences through them, then use those embeddings, the things that will come out as we'll see at the end, to do classification. And so there was like kind of the idea that all the information was baked into the model, and then you could use a discriminator on top. And so those sometimes called adapters. People do use those all the time if you have a specific choice as a good representation. That is now also widely used in places like stock trading and other places. Weirdly, they've started to use models that look like that, not BERT models, but backbones to be able to have a model which is trained kind of generatively, gets a good representation of the space, and then the terminology is fine-tuned for the particular application. And I think we will do fine-tuning in like the last weeks of the course. But yeah, you got the picture. You're exactly right. Took us decades to figure out, but like it's kind of obvious in retrospect. Cool. Other questions? Awesome. Let's talk about spam filters, I guess. All right, naive Bayes, a generative model for discrete features. Okay, so GDA is going to work over continuous features, but what if the features are discrete? Okay. Oh, please. Please, yeah.
I know that you said that the significance of the GLI family was that we have this natural parameter that we're modeling linearly, and so if we can represent these different models under this formulation, we get inference for free.
Right.
Is there something analogous here? That's
wonderful question.
Why we get, what's representing a generative family down here?
Yeah, okay, this is a wonderful question. So the question was, we sold you GLMs, or I sold you GLMs because I was like, oh, they're all, it unifies all these statistical procedures. Isn't that nice? And that's pedagogically quite true. And so you'd ask, in this kind of generative world, is that also true? Is there something that kind of looks like that? And in some ways, yeah, you use Bayes rules and all the rest, but it's much less operational. They don't all have the same form. The models underneath the covers seem to require little bits of how you set them up. And they lead to different lines of thinking. One is like these graphical models, which we'll talk about very briefly. And then others are these more complicated backends. So it doesn't have the kind of clean simplification where all of that line of work can be kind of put in a nice bucket. Maybe it will in like 5-10 years, or someone will figure out like, hey, here's a nice way to view all of these things in the right abstraction. But to my knowledge, there's nothing that's really a competitor there to do that. Wonderful observation. Cool. Others? Awesome. All right. Okay, so back to the questions on discriminators. There are places that you would want to use this. This is one of the great places to use the models as we were just discussing before. You want to do spam or email classification, then using one of these BERT-style models, so-called bidirectional models, to go through and do an encoding and then do a classifier is actually a great representation. Sentiment analysis, is this positive or negative? But we'll talk about the simplest way to do it, okay? Same rule. Model px given y, py, classified by Bayes rule. Okay? This will again be kind of a dirt cheap way to do it. So the idea is we're going to build a dictionary of the top words from the training corpus. These are the kind of, think about top as most informative. Okay? So what does it mean for a word to be most informative? Well, it doesn't mean the most frequent, like the, a, and what are called stop words. You probably don't want to put into your vocabulary, right? Because they don't give you a lot of signal. But maybe, they have, there's words that are very highly loaded for various sentiment. I hate this thing, whatever, right? Claude's list of curse words. Yeah, right? Whatever. Okay? So you have that binary vector. And that binary vector is that each one, you're going to put a 1 if it's there, which is called a 1 hot, or 0 otherwise. Okay? Right? All right. So for example, by free meeting C29 homework, this is what you would get if these were your 5 words. This is how you would featureize. This last part is how you would featureize your text. Okay? Now, as pointed out earlier, the new way of doing this is that instead of having these 0-1 features, you would potentially have features that were learned or whatever, but this is the simple standard model. And by the way, it's like not that bad of a model. Like one of the things that's amazing about the models of the ancients is that they work pretty well, right? Our new models like sometimes work occasionally quite amazingly, sometimes make really dumb mistakes. Okay, so with d binary features, x could take 2 to the d possible values. So now you have a problem, because if d has like 10,000 or 50,000 words, well, like, what is it, 2 to the 10 to the 300, so like 2 to the 600 is like the number of atoms in the observable universe, like we're toast. We cannot represent this, okay? We can't write it down. So we can't possibly model this as a full multinomial. So what are we going to do? Well, we're going to make a simplifying assumption about our data. We're going to assume that these words are emitted effectively independently. We're going to make a different kind of independence assumption. And we're going to assume that they're developed conditionally. So what it's going to say is the probability that xi, x1, xd are actually emitted are going to be independent, conditional on y. So given the class, given the sentiment, the words you use, you may pick which words to use independently. We're not going to make any assumption on that. And clearly they're not independent. But we're going to assume that, and we're going to be able to factor the probability distribution in this really nice way. And that's going to let us go from having 2 to the d examples to having something much smaller, d. Okay. So the chain rule says you can factor in this way, where you're continually adding context. But this drops all conditioning on other features. What it basically means is another way of saying you don't care about the probability that you use one word and another. So in particular, if you said, you had some negation and they're not something, right? It's not the worst, right? It's not super positive, but it's the worst would get highlighted and the not would get highlighted and they would get multiplied together, right? And not you would probably dry because not has a valence to it. So it wouldn't fit into this. So you don't condition on those two features. Everything is treated effectively conditionally independent. Okay. Now, how does this work? So you have some prior probability, the probability of spam in this case, right? That your likelihood is going to be there. You have exactly the same kinds of conditional distributions that we saw previously. Given that it's spam, what's the likelihood that it has a word, right? Whatever spam has gotten much better, but like whatever spam you've seen recently, I don't look that much in my spam folder, but like, if you look in there, you'll see what they're trying to sell you or whatever, introduce you to or whoever, you'll be there. So you have those words. And then you'll have a bunch of words that are in non-spam, right? Like, I don't know, faculty meeting. But they start putting that in spam, we're all toast. Anyway, okay. So this only has now order d parameters, 2d plus 1. Why? One parameter here, because there's two classes. And d parameters to represent each of these. Why d parameters? Because you need one weight for every term in every class. Right? So you have d terms, two classes, 2d. Instead of 2 to the d. So we've gone from exponential to linear. So far, so good? All right. All right. So how are the estimates? Well, no surprise. How do you estimate the fraction of spam? You count the fraction of spam. How do you estimate how many words contain, spam emails contain the word J? Well, you look at all the spam emails. You see how many contain the word J, and you divide. That's your fraction. And all of these are most likely estimates. And it's just like GDA. It's dirt cheap to train, even on huge corpus. And it's surprisingly accurate. And inference is dirt cheap as well. You just look at the vectors, you look them up, multiply them, done. Or you take the logs and add them. Either way. Clear enough? So this is a very efficient model. And this is how you classify, just like that. You look at the two things, you take the logs, you add them up. Boom. We talked about Laplace smoothing. This is the magic. We add some ones. Feels good. All right. And I can make a more fancy version of that. We're going to talk about regularization on Wednesday. But the basic thing here is it prevents zero probabilities, and it shrinks your confidence in estimates. And we'll talk about various forms of regularization that basically make the model less confident about what it's seeing. This is a very simple smoothing form that actually gives, interesting, appreciable results. You can use other numbers there too. It's not a big deal. All right. So these are the two generative models that are there. And then I want to summarize and get you out of here on time. So we introduced these generative models. We classify via Bayes rule. We talked a little bit about Gaussians, 1D and 2D. We derived GDA, which was the Gaussian discriminative analysis, where everything was class conditional Gaussian. We then did class conditional naive Bayes on discrete features very briefly. And in both cases, we had these nice closed form maximum likelihood estimators. I did not derive the maximum likelihood estimators in the second case, but the proof is identically the same. You set up the logs, you compute the derivatives, and you get a bunch of equations that you can very easily solve. We did a little bit of matrix multiply and other stuff that was there. If that was unfamiliar to you, take a look at that. In the next class, we're going to look through data sets and other things there, and we're going to talk about training sets and test sets and all kinds of fun stuff. Have a great rest of your week.